All right, let's pick up where we left off last time with our Chapter 3 review problems. We're going to pick up with number 79 from the textbook. And it says that the cost C in dollars of producing X units of a product is given by the equation C is equal to 0.75X plus 4,000. And we're asked to find the average cost. So part A says find the average cost, which is 0.75 plus 4,000 over X. And then we want to find C bar when X is 100. It's 0.75 plus 4,000 over 100 is 40.75, and this is dollars per unit of production. And then when X is 1,000, 0.75 plus 4,000 divided by 1,000 is 4.75. And the question here for part C is to determine the limit of the average cost function as X approaches infinity. Limit as X approaches infinity, 0.75 plus 4,000 over X is 0.75 plus 0 as that goes to 0 as X goes to infinity is 75 cents per unit. And what does that mean? Interpret that. So that means that there's a fixed cost of 75 cents per unit. And this other piece over here is the variable cost that can be scaled by economies of scale. And we can get that to diminish. It'll never go completely away, but that part approaches 0. And we're left approaching the fixed cost of 75 cents per unit as we produce more and more. So we'll never get there, but we'll get closer and closer to it. So let's go ahead and look at number 80, which is a similar question. Cost C in dollars producing X units of a product is C is equal to 1.50X plus 8,000. So again, we want to find the average cost function, C bar, which is equal to 1.50 plus 8,000 over X. And for B, they want us to find C bar of 1,000 is equal to 1.50 plus 8,000 over 1,000 is 9.50, and that's per unit of production. And then C bar of 10,000 is 1.50 plus 0.80 will be $2.30 per unit. And then for part C, we want to find the limit as X goes to infinity of 1.50 plus 8,000 over X will be 1.50 plus 0 is $1.50 per unit. Again, that represents the fixed cost that will approach. The 8,000 over X represents the variable cost. This is per unit. And this variable cost can be diminished with economies of scale, but the fixed cost remains constant no matter how many units we produce. So that's our ideal that we can approach, but we just won't get there. Let's go ahead and look at number 81 now from the textbook. Just review. Talks about the cost of seizing P% of the illegal drugs in the country, giving the function 250p over 100 minus p, where p is a percentage that is between 0 and 100, and c is in millions of dollars. So when we get this answer, we want to give our answer in millions of dollars. So first, let's find the cost of seizing 20% of the drugs in the country. And I'm just going to go ahead and put this formula in here. Alpha y equals n over d, 250x, and then the bottom is 100 minus x, and go to my table, and we want 20, and let's go to my mode, and I want my answer to always come back as a decimal. Here, so that's 62.5. Remember, these are millions of dollars, right? So C of, and then 50%. So if we were to try to seize 50% of the drugs, we would have to spend $250 million. And if we wanted to seize 90% of the drugs, we would have to spend $2,250 million, which is the same as saying 2.25 billion dollars is what that would be. $2,250 million dollars. And you'll see that there's an asymptote here at 100. It's a limit that we can approach, we can't touch. So that's kind of part B, asks us to find the limit here as x, or as p approaches 100 from the left, number that's a little bit smaller than 100%. So this is going to be getting close to 250 times 100. It's 25000. And then this number is getting close to 0 from the right. So a positive number divided by a very small positive number is going to go to a positive infinity. And what does that mean for us? That means that the cost of this is going to increase with that bound as we try and approach 100%. So just write my answer similar to how the book did here. The limit goes to infinity, meaning that as the percent gets very close to 100. The cost grows without bound. And what this tells me is that there's a theoretical ideal of approaching of seizing 100% of the drugs, but we're never actually going to get there, and it's cost prohibitive to do that. That we get this idea where we're going to have to say we're going to have to do a cost benefits analysis in this case to say, okay, what level are we okay with leaving out there, because as we get closer and closer to trying to seize 100%, look at how much it's growing. It went from 62.5 million at 20% to, which is already a big number, to 250 million. Maybe, you know, in government projects and things like that, that's not so bad. But now to try to get 90%, and we're spending $2.25 billion, no, right? People are going to balk at that, probably. Anybody that tells you that the answer is just to throw more money at the problem is not necessarily being reasonable. So we have to consider that when we're considering cost benefits analysis like this. All right. So let's move on to number 82. Similar problem, but now let's look at removing pollution, removing pollutants instead of removing drugs from the country. So this is a private company here. The cost C in dollars of removing P% of the pollutants in the stack emissions of a utility company that burns coal is modeled by C equals, and then this is 160,000 P over 100 minus P. Again, P is a percentage that's between 0 and 100. And now C is just in regular dollars. So, but now your thought process needs to change, because we're dealing with an individual company now. We're not dealing with the whole economy of the country. So let's go ahead and change our formula here. And we're going to say 160,000 X over 100 minus X. And we're going to be asked to find the cost for 25% removal. And that is $5,333.33 approximately. It comes out with a third of something, so we can say it's exactly that. And then C of 50, it's going to be, I already have 50 here, so that's exactly 160,000. So we're now at $160,000. And then we're asked about C of 75. So let's make this a 75. And we get 480,000, right? Now, if you were the company, I mean, you're going to have to obey regulations and things like that, but look at how much this jumps up, because this is a rational function with a vertical asymptote here. Look how this just takes off. The first 25% only costs you a little over $5,000. The second 25% here costs you over 150,000, close to $155,000 to get that second 25%. The third 25% here costs you over $300,000. So you have to consider this cost benefits analysis here, and to get even that tiniest little bit of change as you approach this asymptote is going to have a huge marginal cost for you if we would be taking the derivative here, and you would see that the little tiny changes would still have huge costs to them. And that's something that needs to be considered, as how good is good enough in this type of a situation. So as we talk about the limit here and what it means, we've already talked about that a little bit, but limit as p goes, or as p goes towards 100 from the left of this function, 160,000 p over 100 minus p is again going towards 160,000,000. So that's 16 million up there, over 0 from the right is going to go towards a positive infinity. And so the limit is going to infinity. Meaning that as the percent approaches 100, say it gets close to the cost increases without bound. All right, that was number 82. Let's move on now and look at number 95. And number 95 starts off with a table here of t and n values. Give myself plenty of space here. 1, 2, 3, 4, 5, 6, 7, 8. These numbers get kind of big, so that's why I'm giving myself some space. So it starts off 25, and then it goes to 200, and then 804, 1756, 2296, 2434, 2467, 2473. All right, so that is the observation of the size of a bacteria culture after, I think it's T is measured in days. Yes. So it can be modeled by this equation using statistics. And and we're told that T is between 1 and 8 for that model, because that's our chart right there, right? So really this model, we only know for sure that it works within the data that we were given. So first things first, they want us to graph that equation, alpha y equals, and we want 2, 4, 6, 7, 0 minus 3, 5, 1, 5, 3, and we're going to use an x instead of a t, minus 1, 3, 2, 5, 0 x squared over 1, 0, 0 minus 39 x plus 7x squared. And let's see here. I didn't give myself any bounds for this in the window, so let's go ahead and I know that I'm not going to have a negative number of bacteria. It looks like I can go up to 3,000, probably even 2,500. Looks like a good upper bound here. I'm sorry, that's my my x. Let's go to 10 on my x here. And I want to go 0 to, like I said, 3,000 or 2,500 by, let's say, 100s here. And so let's just look at my numbers here. If I put in 1, do I get 20? No, I typed in something wrong. So 24670 minus 35153x minus 13250x squared divided by 100 minus 39x plus 7x squared certainly is what it looks like they said in the book. But that is not modeling my data that I was given. Not in the slightest. All right, let's look and see if it gets to be better here. As I go on. No. It's getting more and more negative as I go on. So it looks like there's an incorrect sign here. This is supposed to be a positive sign. That's what's wrong. It's all the difference in the world there. There we go. So I need to make my window go a little bit higher, maybe to 3,000. Like I said. All right, there we go. And so use the graphing utility to create the scatter plot of the data. So let's do that. Let's turn this off for a second. But let's go into stat, edit, and let's put our data in here. So we want 1, 2, 3, 4, 5, 6, 7, 8 in L1 that will be for our days, and our population of our culture or colony there will be right here. So 25, 200, 804, 1756, 2296, 2434, 2467, and 2473. So we want to second stat plot, turn plots on, and we want a scatter plot with X being L1, Y being L2, and just use that first kind of mark. It doesn't matter what color you make it if you have colors, and just there's the plot. And then we want the graph of the data to be turned on as well in the same viewing window as that scatter plot, and see how they got the equation that approximates the data. I won't tell you how they did it. That's for you to learn in other classes if you need to, but that's one of the models that we have in statistics to use. So how well does the model fit the data? It fits very well. Statistically speaking, I wish I could run you through the statistical analysis to get a value R squared that actually tells you what percent of the change in output is explained by the change in input. It basically tells us in some ways how good our model is, whether it's a very strong correlation or not. We can look at that R value. This would have a very strong correlation though. So let's go ahead and then use that model that's there. Since it's a good model, we should be able to use it to predict things. So let's predict what happens at day 10. So at day 10, we can make a prediction. It's not perfect, but we can predict that n of 10 will be 2, 4, 3, 4 bacteria. The next bacteria hasn't split yet, so we don't, even if that had been a 0.5 or above, we probably wouldn't use regular rounding rules. We would probably want to round down. And the question is, should we use this to predict the number of bacteria in the culture after a few months? Why or why not? So I say no, because the further that we get away from this data that we have, the more uncertain we are about the fact that things are going to behave in the same way that they've been behaving. There's even some level of uncertainty here going to 10 because it's outside of our interval of 1 to 8. So we have to give some uncertainty in our answer for 10, but we would have to give a lot of uncertainty if we're going to go months out, if we're talking about 3 months, 6 months, 12 months, whatever. Now, it may be the only data that we have, and then we have to report it that way with lots of uncertainty. But if we want to be able to make better predictions over longer periods of time, then we need to collect a lot more data. 8 days worth of data would not probably be good enough to predict something several months out. We would probably want to collect at least a month's worth of data, right? Maybe more than that. If we're going to go out to years, we might want to collect 3 to 6 months worth of data. So you get the idea that this amount of data is probably sufficient for predicting what happens in 10 days, but it probably would be okay for predicting what happens in, say, 30 days, but I probably wouldn't want to use it to predict what happens in 60 days, 90 days, 120 days, 365 days, something like that. I'm probably getting way outside the scope of what I should be able to predict with that little bit of data that I was given. All right, let's go ahead and look at number 96. And you have a suggested answer in the back of your book for C that basically says this. And it's an okay answer, but I don't really like it for the reasons that I said. They said that if we're going months out in advance, we might as well call that infinity because we're so far away, and we could take the limit of this as t goes to infinity. And we can see that this has a horizontal asymptote here. In this case, because it has a horizontal asymptote, if this model holds, it should hold that we should be approaching and they do use regular rounding rules in the book. I don't like that they do that, but that we're approaching a colony size, a culture size, 1,893 bacteria as we go out a long period of time away. All right, so yes, I get what they're trying to do to make you think of in terms of 8 days, that months, years, decades, whatever would be basically infinity to you at that point. And you can look at this rational function and say it has a horizontal asymptote, and you can find it, but just general statistical principle that's good for you to know in business or any other natural applications or whatever you're going to be using this calculus for, is that you stay as close to your data as possible when making predictions. So if you are making a business plan for 5 years in the future and you use your previous 5 years, that's acceptable. If you start making a 10-year plan from that, give yourself quite a bit more uncertainty, right, on what's going to happen in the next 10 years. If you use 5 years of data previously to start talking about what's going to happen in the next 25 years, now you are probably going to be in trouble putting a lot of stock in that model, and you're going to need to come back and readjust that model a whole lot. Maybe every 5 years or so, you need to take the new data and see if it changes your model. So short-term forecasting is much better modeling than long-term forecasting. Let's talk about that a little bit now with meteorology, where we do a lot of forecasting. And the monthly average high temperature, capital T, in degrees Fahrenheit for New York City can be modeled by the equation capital T is equal to, and it was kind of cut off on my paper, so I wrote it down here. 31.887 minus 1.7686 T plus 0.09031 T squared divided by 1 minus 0.1924 T plus 0.01286 T squared. And T has to be between 1 and 12 because it's the monthly high temperature, and the months are 1 for January, 12 for December, and so on. So let's graph the model here with the calculator. We're not going to have any plots this time, so I'm going to turn those plots off. If you have a calculator that has those option turns plots on and off from your y equals menu, go ahead and do that. Otherwise, you have to go back into your stat plot menu and turn your plots off there. Y equals, and then if you have the alpha y equals n over d, that's great. If not, make sure to put parentheses around your numerator and parentheses around your denominator here. 31.887 minus 1.7686x plus 0.09031x squared over 1 minus 0.1924x plus 0.01286x squared. And we're going to graph this, and it looks like, I'm just going to figure out part of the answer here to help me figure out how high my graphing window needs to be. Okay, so my window just needs to go maybe between 0 and 10 by ones. And no, let's pick a reasonable for the temperatures. Let's go between negative 15 and this is New York City, so that's why I'm picking such a low temperature there, and maybe 100 for the high. Let's go in, let's make this negative 20. Let's go by tens, and this is going to be 0 to 12. Okay, so let's graph this. All right, there we go. So they don't have any negative average, what were the average high or average low temperatures, or just average temperature. This is average high temperature. Okay, that makes sense. So graph the model and find all of the absolute extrema. So the lowest high temperature appears to be in January. Let's just verify that. Let's look at 1 and let's look at 12 because those are both kind of low. And that 36.8 is our absolute minimum. So our absolute minimum is T of 1 is 36.8. And then our absolute max, we'll use the calculator to find that. So maximum is going to be up here. Absolute max is at 7.27 and is 84.7. These are degrees Fahrenheit. So it happens after 7 months, so past the end of July, in early August is when the highest high temperature is in New York City, is what that's telling me. So that was the last part of the problem, is interpret the context here. So that tells me that I should expect high temperatures, probably between the high 30s and mid 80s in New York City. Probably would be safe to say that I would expect T to have a value between 35 and 85. Like that would be a good expectation. And where that's the high temperature and the lowest high temperature I would expect in January, and the highest high temperature I'd expect in August. Okay. There could be some variation in that because this is just a model. It's not what the data is actually going to do, just our best model of the data that we have right now that we will use to predict what we think it's going to do. Let's go ahead and look at the next problem here. Let's actually save these next problems for another video because we have lots of marginal analysis problems to come back to, and we'll do those all in their own video next time. So I'll stop here, and next time we'll come back and talk about problems 101 through 106, and we'll just do those as their own video. So 101 through 106 next time. See you for the next video.